the clue is obviously in the title. We're looking at projectile motion for this question. So let's have a read of the context. All right. During a cricket game, a batsman hits the ball at an angle of 40 degrees to the ground, with a velocity of 20 metres per second as shown below. All right. Show the initial vertical component of the ball's velocity, 12.9 metres per second. So we are aiming to get this as our answer. This is only an achieved question, okay? So we cannot use this 12.9 in our calculations. That is the answer we should be getting to, okay? But you can't use it to work it out. So what we need to do, all right, is we're needing to find this vertical component here, all right? So our vector triangle is going to look something like this, okay? We've got an angle of 40 degrees here. This hypotenuse is 20 meters per second, and we're trying to find out this one, the vertical velocity, okay? So we're going to need to use some trigonometry, all right? Because we've got the hypotenuse and the opposite, all right, we're going to use sine. Remember, so katoa, so we're going to use sine because we have the opposite and the hypotenuse. So the vertical velocity is going to equal 20 meters per second times by sine 40. Now when we do this in the calculator, please remember to check. Here your angle is set into degrees, not in radians. Okay, so 20 times sine 40 should give us what we're trying to show, an answer of 12 meters per second. Okay, so 12.9. So that's our show. All right, this is our guide of where we should end up. Okay, so we should end up with 12.9 meters per second. All right, now that's just our achieved question. That's just starting us off. All right, question B, calculate the time it takes the ball to reach its maximum height. Okay, so what information do we get out of this? Well, first of all, we're wanting to work out time. So that's our question mark. Okay, what information do we have? So we've calculated, or they've told us, that our initial vertical velocity is 12.9. All right. We then need a couple of more bits of information to be able to use our projectile motion equations. Okay, so we know that at the top of any projectile motion, all right, the vertical velocity will be 0, right at that very top. So because we're wanting to work out the time it takes to get to the top, our VF is going to equal 0 meters per second. All right, but we still don't have enough information yet. We do have one more piece of information, and it is resource sheet, okay? And it's this bit down here. So we're needed use G equals 9.8 meters per second squared, okay? Now we can actually put another letter in there. That other letter can be A. So we do actually have an acceleration, right? That is gravity, okay? So that's looking pretty promising. We've got a lot of stuff. So let's take a look at our projectile equations up the top. All right, we're wanting to find T, we have a VI, we have a VF, and we have an A. We don't have a distance. VF equals VI plus AT is the equation that we're going to use. But we're wanting to find T, and that's on the wrong side of our equation. So, again, you can either rearrange first and then substitute, or substitute then rearrange. I'm a rearrange first kind of person, but it's up to you. All right. So we're wanting to get T by itself. First step is we're needing to get rid of this VI, get it to the other side. So because it's being added to AT, we've got to minus it. So VF minus VI equals AT. All right. That seems pretty easy. Then our next step, we're going to divide by A, and that will leave us with T just by itself. So VF minus VI divided by A equals T. All right, now we can substitute in. So T equals, our VF, remember, is 0. VI is that 12.9 that we got given. And 9.8 is our gravity. And that'll give us a time of 1.316 seconds. Now, on my calculator, it's actually showing a negative, okay? And that's because I've got a negative 12 from 0 minus 12, okay? And then I've got 9.8. So there are two ways around this, all right? You can put a negative in front of the 9.8 to show direction because it's going down, okay? Or because you're not going to have a negative time to travel to the top of your projectile motion, all right, we can just ignore that little negative there for now. We're going to need to make sure that it's the right number of significant figures. So we're going to need to get it to 3. Now, this bit's a bit tricky because you might say, but the gravity is 2. And yes, the gravity is 2, but it actually does have more significant figures. But for level 2, we don't use those significant figures. So for here, we have a time to the top of 1.32 seconds. Okay. Now, because we've rearranged, because we've used some previous information, we're getting to a merit with that question. Part C. Calculate the horizontal distance, that's important, travelled by the ball before it hits the ground. There's a couple of things we need to think about here. We can no longer use gravity as an acceleration because that only happens in the vertical, that only happens up and down. We're looking now in the horizontal, the left to right. So that doesn't apply anymore. We don't need that acceleration. All right. Now, in the horizontal component of any projectile motion, our velocity is going to be constant. Okay, so once it's been hit by the bat, there are no external forces happening in the horizontal component. Okay, so we have a constant velocity for that horizontal part, okay, which we need to work out. So we're now going to work out this arrow down the bottom, okay? So we're going to use our hypotenuse again, and now we're going to use our adjacent, all right? So that means we're going to need to use cos, okay? So the ka of SOHCAHTOA, we've got the adjacent, we want the adjacent, and we've got the hypotenuse, okay? So the velocity of the horizontal, that's going to be important, is going to be 20 cos 40. We're going to get a horizontal velocity of 15.3 meters per second. All right, that's our first little bit. Then we need to work out how long it takes for the ball to get from the bat, fly through the air and hit the ground. All right. So if we look back at B, we can actually see that we've already worked out half the time. We've got the time it takes to go from the bat to the top. And it's going to take exactly that same amount of time to get from the top down to the ground. Okay. So we can take this time here, 1.32 seconds, from the bat to the top, and times it by 2. So we go back to the top and top to the ground. And that's going to give us 2.64 seconds for our total time. Now, because we're in the horizontal component and we don't have any external forces, we've got no accelerations going on, we can just use that plain old equation. Velocity is distance divided by time. Okay. So velocity is distance divided by time. We've got a velocity, we've got a time, we want to work out distance. Perfect. Okay, so we just need to rearrange. Distance equals velocity times time. So we're going to do 15.3 times 2.64, and we should end up with 40.45 meters. It's actually 40.447. So what we're going to do when we round to our significant figures, all right, we've got 3 here and we've got 3 here, so we're going to have 3 in this question. It's going to be 40.4 meters. Now, you might also get 40.2, and that would be if you used your unrounded time here. Okay, so let's go back and have a look what that might look like. So 12.9 divided by 9.8. There's our unrounded value. We're going to times that by 2 to get the total flight. Okay. And then we're going to times it by that. So we're ending up with 40.2 or 40.3. Okay, so it just depends on whether you use unrounded or rounded. Now you should always use your unrounded. Question D. So we've done a bit of projectile motion. We've worked out some distances and times. We've done some trigonometry. Let's have a look at question D. All right, so give a comprehensive explanation using your words of the effect of the forces, more than one, acting on the ball during its flight. Now, this is important. We're going to assume air resistance is negligible. Basically, that means it's almost zero, so we're not going to worry about it. So air resistance or any kind of that friction stuff is not going to apply here. Okay, so we've got 4 bullet points to help us in our answer of explaining the effects of the forces. So what we should do is we should talk about the horizontal motion of the ball. We should talk about the effects of forces on the horizontal motion. And then we need to do those same 2 steps for vertical. Okay, so in the horizontal, the horizontal velocity, so VH, is constant once the ball has left contact with the bat. Okay, and this is because there are no external forces. In the horizontal acting on the ball. Okay, so we've sort of done 2 bullet points in one sort of sentence here because the horizontal one is a relatively easy one to explain. So horizontal motion, that velocity is constant once the ball has left any contact with the bat because there are no external forces acting in that horizontal direction. Okay. We have assumed air resistance is negligible. Okay, so that would be the only force that would be acting in the horizontal, but because we're assuming it's so small it doesn't happen, there's no external forces. All right, now let's move on to the vertical. So vertical, we do have accelerations because we do have some forces. Okay, so we've got 2 parts to our projectile motion, going up to the peak and then coming back down to the ground. Okay, so let's do going up first. So the vertical motion going up, that's our first part. All right, so as the ball goes up, the vertical velocity decreases, or you could say decelerates, at a constant rate due to gravity. And I would put in there 9.8 meters per second minus 2. Okay. So the force that we're talking about is the weight force or gravity. This weight force acts in the downwards direction or acts down. In opposition to the ball's vertical motion. So the ball's trying to go up, okay? That's where its vertical velocity has come from. And so that gravity is acting in the opposite direction. So we're going to slowly decrease the vertical component until we get to 0 at the top. Okay. All right. Coming down, it's basically the opposite thing. So as the ball falls from the top or maximum height, we can say basically the same thing but opposite. The vertical velocity increases or accelerates at a constant rate due to gravity. All right. Which is acting down or downwards. This is the same direction as the ball's vertical motion. All right. So here, because they're acting in opposition to each other, we get this sort of minusing effect where our vertical velocity gets smaller. And when it's falling, our gravity and the ball's motion or direction of motion is acting in the same way, so we get this additive. So we're increasing the ball's overall velocity. All right. So we've talked about horizontal motion. It's constant or horizontal velocity. We've talked about forces. There shouldn't be any effect. Okay. So we've ticked those. We've described vertical motion in two parts. So we've talked about as it goes up, the velocity decreases, and as it goes down, the velocity increases. So check. We've also discussed the effect of forces on that vertical motion. So as the ball goes up, the velocity decreases due to gravity. So here's our reasoning, due to or because of gravity. Okay, this is some further reasoning. So this gravity or the gravity acts down, which opposes the vertical motion. So that's why we get the deceleration. Okay, so that's where we start getting the explanation, is when you're starting to use words like because or due to or therefore or which. So all of those linking words are starting to explain your ideas. Okay, and so when we do the same thing for here, all right, if we get all three of those explanations nice and solid, we've got an excellence.